Hello friends, welcome to the second lecture of digital communication. In the last lecture, we have seen the basic introduction of digital communication. Now today, we want to see the basic process at how we can convert our analog signal to the digital signal, right? And the process involved in the conversion of analog signal to digital signal is sampling and quantization right? So today we are going to study what is sampling and what is quantization, right? So if we see the objectives today, we will see what is sampling, what is quantization, and what is the Nyquist criteria, because it is very important in sampling. So this is again very simple, that we always have analog signals at the input side, right? And we have to convert these analog signal into digital signal. So when we are in the process of converting an analog signal into the digital signal, then first we have to do sampling, and then we have to do quantization, and again in the third part we have to do encoding also, and after that we can get our digital signal in correspond to the analog signal, right? And this is also important that we have to do the sampling in a way that we should recover the signal at the side of receiver. Why? Because at the transmitter, what we are doing, we are converting our analog signal to digital signal, and this digital signal is moving into the channel, right? And at the side of receiver, we are receiving digital signal, right? And at, for example, this is our antenna or this is our receiver. So with the help of this receiver, we are receiving digital signal, and but we know that at the transmitter side, the original signal was analog in nature. So ultimately, we have to convert our received digital signal back to analog signal so that it can be properly understandable to the end user, right? So this is important. Means transmitted signal was analog and received signal will also be analog. In between, we have to do analog to digital conversion, and again back at the side of receiver, again we have to convert our digital signal back to the analog signal, right? So it is very important that the signal should be digitized, digitized uh, with some criteria, so that it can be successfully recovered back into the analog form, right? So that criteria is basically defined by Nyquist. So we will also see the criteria which is named as Nyquist criteria for proper sampling, we can say that we have to study the sampling, we have to study the quantization, because these two processes are involved in the process of digital conversion. And then we have to understand what is this Nyquist criteria, so that the signal which has been digitized, it can be successfully recovered back, right? So this we have to understand today. Now we can start with simple sampling theorem, or we can say we can start with simple sampling process, right? Simple sampling process, right? So we can see here a band limited signal having no spectral components above FM Hertz can be determined uniquely by a value sampled at the uniform interval of Ts seconds, right? So what is the sampling theorem? Actually, when we are having our analog signal, for example, this is our analog signal, and we have to convert this signal, or we have to take the sample of this signal. For example, we are taking a sample like this. These are few samples. How these samples we can get, I will show you later. But till now, you can see here that, for example, this is the sampled version of this analog signal, right? So sampling means at what rate we have to break this signal, right? At what rate we have to pick the values of this analog signal. See, whenever we want to do sampling, it means that at all values of time we are not interested, right? At all values of time we are not interested. For example, this is our amplitude axis and this is our time axis, right? This is analog signal. Why? Because it is continuous in time domain, right? It means a signal will be analog. Why? Because it remains, it exists, it exists at all the values of time. It exists at all the values of time. But when we want to convert this signal into the digital signal, what it means? It means that the signal should be discontinuous. The signal should be discontinuous in time domain. In time domain. So this is important. Signal should be discontinuous in time domain. So discontinuous means that you are not interested. You are not interested in the means at all the values of time for the signal, right? You don't want the signal at all time. You want signal at some points, at some times, right? For example, here you can see this waveform is a analog signal. Why? Because it exists at all time values between 0 to t, for example, right? Between 0 to t. But here in this signal you can see that the signal is existing only at few time instants. For example, this is t0, this is t1, and this can be t2, right? And so on, right? So you can say that we have break the time domain to get the sampled version of the signal, right? So what this sampling theorem says? Sampling theorem says that the sampling frequency means the rate at which you are cutting the time axis. That sampling frequency should always be greater than or equal to twice of fm, where fm is the frequency of analog signal. fm is the frequency of analog signal, right? For example, this is a signal of having frequency fm, then the rate of sampling should be twice of fm. Or in other words, in time domain, what we can say that sampling time should always be less than or equal to 1 upon twice of fm, right? So for example, here we can say that if the frequency of this signal is fm, then you can say that the time period of this signal can be equal to t, which is equal to 1 upon fm, right? So the sampling time ts should always be less than or equal to t by 2, right? So this is the sampling time. Means at least if you are doing sampling at t is equal to t naught, this is your first sample, then for the second sample at least you have to wait for this time. At max you should wait for this time, right? It should be ts is less than or equal to t by 2. So maximum value is what? Ts is equal to t by 2. Otherwise it should be less than capital T by 2, right? So in this fashion you can take the samples of the analog signal, right? So I hope the concept is clear now. Again I am repeating, what is the meaning of sampling? Sampling means that you make the continuous time domain discontinuous in time domain. You make the continuous time domain of any signal discontinuous in time domain, right? It is basically sampling. So it means that you are interested in the samples of this signal, not in the whole signal. Right? You are interested only in the samples of the signal. So at what rate you should pick the sample? At what rate or the frequency of the picking the sample should be greater than or equal to twice of fm in frequency domain. Or if you want to talk about time, then sampling time or sampling interval means if you are taking first sample at t is equal to t naught, then what should be the time of second sample? At max it should be equal to capital T by 2. or always it should be less than capital T by 2. If it is greater than capital T by 2, you cannot recover the signal at the side of receiver successfully, right? Means you get somewhat noisy signal. So this is very important. And the operation which performs sampling is known as sample and hold operation, and output of the sample and hold circuit can also be named as pulse amplitude modulation, PAM. For example, this signal, this signal can be named as PAM, because it is pulse amplitude modulation. The value of amplitude of any pulse is changing according to the massive signal. That's why it also satisfies the definition of PAM, right? Sample and hold. Output of sample and hold circuit is also can also satisfy the definition of PAM. That's why we can say that the signal is pulse amplitude modulation. Now, to get more better understanding of sampling, we can see this circuit. This is a very important circuit, right? Here we can see it. For example, here this is analog signal. You can represent this analog signal by xt, and then you have a low pass filter. This LPF is low pass filter, so definitely the output will also be analog signal, because filter is just passing the signal and it is stopping the undesired frequency range. So it just pass the analog signal and stop the undesired frequency. So the output will again be analog signal, and to make this signal digital, what you have to put? You have to put a sample and hold circuit, right? So the input of this sample and hold circuit is the analog signal, which can be named as ST, and then the output, this signal, right? It can be the sampled signal, which can be named as SST. SST means the sampled signal, right? The sampled signal. So here this is very good waveform which can show you how we are doing sample and hold operation. So for example, here this is our waveform, right? This is our waveform, and now what we have to do? We have to take the sample of this waveform. So what this sample and hold circuit will do? It basically, for example, this is sample 1 and this is sample 2 and this is sample 3, right? I should make it large so that it should be more visible to you, right? It should be more visible to you. So for example, this is the analog signal. So this is my first sample, this is my second sample, this is the third sample, right? So what the sample and hold circuit will do? Actually it do sampling and then it hold the value till the next sample time, right? It hold the value till the next sample time, right? For example, from here, this is the value, this is the sample value, first sample value, and the circuit will hold the sample value till the next sample time, right? So you can say that this is your first sample, and then this is the next sample value, and again this sample value will get hold up to the next sample time. So this is your second sample, right? And then this will be a third sample, and then it can go down, and further it can go down, and further it can go down, likewise, right? So you can say that this is the operation of sample and hold. So hold means this circuit is doing sampling as well as holding the value, sampled value, till the next sample time. This is the main operation of sample and hold. So if any signal is properly sampled, it means it is following the Nyquist criteria. And what is the Nyquist criteria? The Nyquist criteria is Fs should be equal to twice of Fm, right? This is the criteria. Fs should be equal to twice of Fm. The signal can be said as undersampled if Fs is less than twice Fm, and it can be said as oversampled if fs is greater than twice fm, right? But oversampled is not the problematic situation for us, so it is okay, it is okay, right? Again, this is again fs is equal to twice of fm is again a favorable situation to us. So what we can say, that if we do proper sampling, if we do proper sampling, if we do proper sampling, then we should have a criteria fs should be greater than or equal to twice of fm. Mind it, the Nyquist criteria is fs is equal to twice fm, right? If fs is greater than twice fm, it is oversampled situation, but it is not, it is not that much it is not that much uh, means we can say that it is suitable for us, right? It is suitable for us. fs should be greater than or equal to twice of fm. It is suitable for us, or it is a desirable condition. It is a desirable condition, right? So you can either follow Nyquist criteria, or you can be in the position of oversampling, but you cannot be in the position of undersampling, right? This is the problematic scene. fs is less than twice fm. If we do so, definitely there will be losses. There will be losses, right? We'll see what may happen if we have undersampled situation. We'll see it in the next slide. So now we can further we can see the operation of sampling theorem. Till now we are we are studying that what is sampling, and uh, what is the process of sampling. But now we want to see that what is the mathematics of how we can achieve the sampling. We want to see how we can achieve the sampling, right? So for example, here there is a signal xt, there is a signal xt, and this is the frequency domain representation of, this is the frequency domain representation of this xt. For example, this is xt, right? And this is xf, right, which is band limited to minus fm to fm, right? So this is center frequency 0, this is upper cutoff frequency fm, this is lower cutoff frequency minus fm, right? So we can have a frequency bounded signal, so time unbounded signal. So here this is time unbounded signal, right? So this is frequency bounded, or you can also say it is a band limited signal. It is a band limited signal, right? So what we do in time domain, we multiply or we convolute xt with a pulse train, which can be defined as x del t is equal to summation of n is equal to minus infinity to infinity del of t minus nts. So this is the representation of this pulse train. This is what? This is pulse train, right? And we can define mathematically the pulse train can be x of del t, which is equal to summation of n is equal to minus infinity to infinity del of t minus nts, right? This is the equation by which you can represent a pulse train, and then this pulse train will get multiplied to this xt, right? Will multiply to this xt, and then what the value will get? We will get this value. This is a sampled value, xt into x del t, xt into x del t. So you can directly see that the amplitude of this pulse will change according to the value of message. So here you can see that this the pulse at t is equal to 0 will have the highest amplitude. Why? Because this pulse will get stretched, right? So you can see that because here we are having high amount of amplitude, and as we are moving in this direction, the amplitude is getting decreased. So here you can say that the amplitude of a pulse is also getting decreased, right? As the xt is decreasing, in the same fashion the amplitude of the pulses are decreasing, right? Similarly, at this left hand side, you can see this is our signal. So the shape, the amplitude, the value of the amplitude of this pulse will again, or impulse will again change, right? According to the master signal. So this is what? This is a sampling process. So with the help of this pulse train, basically you make this continuous domain time domain signal, to convert this continuous time domain signal into discontinuous time domain signal. So you can see here at this signal you can have the value at every time between 0 to t, right? At every time, for example here at this point, next to this point, everywhere you can have the value. But if you see this signal will have value at x is equal to 0, then at x is equal to ts, then x is equal to 2ts, 3ts, 4ts, likewise, right? So this is very important for us. So this is sampling. This is the concept how we achieve sampling. So if you want to do sampling mathematically, you have just to multiply the signal, your analog signal, with impulse train, right? And you will get the sampled signal. Similarly, if you want to see the sampling in frequency domain, then here we can see that this is a signal which is represented in frequency domain, right? So now again we need a pulse train in frequency domain. So you can see here this is the pulse train in frequency domain, and the representation of this pulse train in frequency domain can simply written as x del f, means the signal is in frequency domain. It can be written as summation n is equal to minus infinity to infinity del of f minus nfs, right? Del of f minus nfs, right? So for example, for 0th pulse it can be n is equal to 0. For 0th pulse n is equal to 0. For first pulse n is equal to 1, and so on, right? So you can simply have del f minus fs, del f minus 2fs, right? Like this. Now in frequency domain, if you multiply this pulse train to this signal, right? So it will generate, this pulse train will generate the impact of shifting, in frequency domain, right? So what will happen, at every multiplication, this whole signal will get shift, right? For example, when you multiply this signal by del f, means n is equal to 0 case, right? N is equal to 0, it will be simply del f, right? So in that case, this whole waveform will be shifted to f is equal to 0. So you can see that this waveform, right? This is the waveform, right? This is the same waveform is replicated here. But when you multiply the del f minus fs to this signal will get shifted from 0 to fs, So what will happen, you just shift the whole signal from 0 to fs. So for example, this is fs, this is 0, and this is fs. The whole signal is shifted towards fs. Now fs is the center frequency. Similarly, if you do for n is equal to 2, then what will happen, del f minus twice of fs. So it means that this whole signal will get shifted to twice of fs. So this is the signal, this is the portion of the signal which is shifted to twice of fs. Same at this side, minus fs minus 2fs, right? So this is the sampling waveform in frequency domain. This is a sampling waveform in frequency domain. So this is basically how we can achieve the sampling. Now this slide is very important to understand that if we are having the sampled output, right, what will happen if we are having the case of oversampling or undersampling. So what will happen if we are having the scene of oversampling or undersampling, right? Oversampling means fs is greater than twice of fm, and undersampling means fs is less than twice of fm. In this case, for example, this is our sampled output. So this is the first pulse, the first signal xf, right, centered at f is equal to 0, and then this is the second part which is centered at f is equal to fs, twice of fs. So this waveform we have already seen, and if we are having oversampled situation, means fs is greater than twice of fm. What it means, see, this gap is what? This gap is twice of fm. This gap is twice of fm. What it means? That next pulse means fs, this value, right? This value should always be greater than this band gap, right? So this gap should be greater than this gap, right? This is very important. So this is fs, from 0 to fs. Fs should be greater than twice of fm. What it means? The next pulse should arise beyond fm, right? Beyond fm, right? So this is the concept, that the next pulse should arise beyond this fm, so that there should be gap between these two consecutive pulses in frequency domain. If it happens, then what is the advantage? That we will not have interference between two nearby pulses or between two nearby signals, right? So we can say that whenever you are following this criteria, then you can avoid the interference between two nearby symbols, nearby bits, or nearby pulses, whatever, right? But on the other hand side, if you do not follow this condition, if you say that my signal is undersampled, fs is less than twice of fm, then what will happen? If fs is less than twice of fm, what it means? That this gap 0 to fs, this gap is not sufficient. So what will happen? This wave will shift towards this direction, right? This wave will shift towards this direction, because it is not greater than or equal to twice of fm, it is less than twice of fm. So what will happen? This pulse will shift in this direction, and ultimately we can have some overlapping, right? In other words, what we can say, that the sampling frequency or the next sampling stunt, right, it is not having sufficient gap. So because of this waveform will shift here, and ultimately we'll get some overlapping area, right? Because next sampling frequency fs, from 0 to fs, this sampling frequency, this gap is not sufficient large. So what will happen? Some area of this pulse will interfere or will disturb with this previous pulse, right? And it is continuously happening with all the pulses, right? So this is overlapping, right? So we can also name this problem as ISI, which is named as inter-symbol interference. Inter-symbol interference, right? So this is very important for us. So this is a very great noise, inter-symbol interference, right? Now we can come to the next slide, which is very important, and this process is known as quantization. We know that we have already done the sampling, and now to convert our signal from analog in nature to digital, we have also to do quantization. What is quantization? It is very much, it will be very much clear with this picture, that for example this is our signal, and we have sampled this signal at different time instant, right? For example, these values shows the natural sampling value, right? Natural sampling value. For example, we have taken the sample at this time instant, right? At this time instant, and the value is this. and the value is this, right? So if we project this value at this axis, right, we found the value which is 1.3, and similarly and some other sample we can have the projected value at amplitude axis is 3.6, is 2.3, and so on, right? What we are doing in quantization, we are fixing the level, we are fixing the amplitude level in the quantization process. See, a signal like this, right? This signal can be named as continuous in amplitude domain as well as continuous in time domain, right? So to convert this signal into digital signal, what we have to do, we have to make this signal discontinuous in time domain as well as discontinuous in amplitude domain, right? This is very important. So discontinuous in time domain, we have already understand the process of sampling, which makes our signal discontinuous in time domain. But to make signal discontinuous in amplitude domain, we have to do the process of quantization, right? So for example, we make the labels, for example, this is our 0 level, and then we found the next amplitude level, it is 0.5, then the next amplitude level it is 1.5, the next amplitude level is 2.5, and next amplitude level is 3.5, likewise, right? So whatever the samples we achieved, we received, right, what we do in the process of quantization, we map these samples to the nearest quantized value, to get fixed amplitudes, So for example, this sample, right, this sample will give us value like 1.3. If you map this the value of the sample to the amplitude axis, it will give you 1.3. But this is not our quantized level. So what we will map this 1.3 to the nearest quantized level at 1.5. So what we'll say, at this sampling instant, the value of the sample is 1.5, not 1.3. This is quantized value. This is called quantized value, and this process is known as quantization, right? So for example, 1.3 will not be the value. The value will be 1.5. The value will not be 3.6. It will be 3.5. For example, at this sample, this is our quantization level 3.5, but the sample value is somewhat 3.6. So what we'll do, we'll map this 3.6 to the nearest possible quantized level. So this is 3.5. So this is our quantized sample value, right? So after doing this quantization, we can say that we can fix some code number, or we can fix some code sequence for every quantized sample value, right? For example, for 1.5 it is code number 5, for 3.5 it is code number 7, for some value 2.5 it is code number 6, and the value of 6 can be written 110, the value of 7 can be written 111, and the value of 5 can be written 101, right? See, we can find out the code for exact number, right? So that's why what we have to we basically fix some amplitude level for a particular code number, right? So for example, for 1.5 value it is 5, for 3.5 value it is 7. So whatever the sample values after sampling, whatever the values we are receiving, for example, it is 3.6, it is 3.65, it is 3.75, it is 3.45, all these value will map to this 3.5. So all these sampled value will quantized, or we map these values at the quantized levels, right? This is the process which is named as quantization. I hope you got the concept. Once we do, it is very easy to do the encoding process to finally convert our analog signal into the bit form. For example, here you can see these are the bits 101, 111, 110, likewise, right? So now your signal will convert it into the bit form, right? So this is the process of quantization. Now further, what we can say that the quantization process can be of two types. One is uniform quantization and the second one is non-uniform quantization. For example, For uniform quantization, we are having, for example, this is a linear quantizer. In the linear quantizer, every time the the gap between two sample is fixed. The gap between two sample is fixed, right? And as the height is also fixed, constant, right? Irrespective of the value of the signal, or irrespective of the information of the signal, right? These in the linear quantization or in the uniform quantization, the gap and the amplitude value is fixed, or it remains constant. But on the other hand side, for non-linear or non-uniform quantization, it can be changed, right? The gap and the step size, right? We say that this value is known as step size, right? And it is normally represented by triangular delta, right? It is represented by delta, right? So this step size delta is constant in uniform quantization, but delta is not constant in non-uniform quantization, and the size of this delta varies according to the amount of information, according to the amount of information or amount of significant values, right? Amount of information, right? This is very important. And if you do non-uniform quantization, then you need some laws, right? So you need laws for what? For means if you want to provide the small values of step sizes, or somewhere you want to provide large values of step sizes, so you need some law so that you can change this height of step size, right? Height of delta. So these law, there are two laws which are very popular. One is known as A law, and the second one is known as mu law, right? So here, sorry, mu law, right? So here you can see that this is the figure. This is mu law characteristics, and this is the figure of A law characteristics, right? Both these quantization process can be followed, and as per the application, right? So at the last, what we can conclude? We can conclude that we get the important insights about sampling. What is the sampling process? Why we need sampling, right? And what is the quantization? And we also got to know that these two things are very important if we want to convert our analog signal into digital signal, right? Into digital signal, right? Or in one line we can say that analog signal is continuous in time domain and continuous in amplitude domain, right? Continuous, sorry, this is continuous in time domain and continuous in amplitude domain. So this is our analog signal. So what we have to do, with the help of sampling, we make this signal discontinuous in time domain, discontinuous in time domain, and with the help of this process quantization, we can make discontinuous in amplitude domain, right? So this is the thing which we have to do to convert our analog signal into digital signal. I hope the concept of sampling and quantization must be clear to you. In the next lecture, we'll see some more interesting things. So kindly be with me for the better understanding of this subject, digital communication. And thank you for patience listening. Thank you very much. Have a good day.